talk to yourself. So welcome to our introduction to networks class, everybody. I want to kind of show you this as something I'm very proud of. We are the Golden Bridge Award winner as of last week, which means we are in North America. So for the United States and Canada, our Academy Sports Center Instructor Training Center was given the highest award possible for all of North America. So
congratulations.
Thank you very much. We're very tickled, and we just appreciate being part of the program, and we appreciate all of our academies that work with us, because we've got 189 academies under us that we work with, and all of them do a wonderful job. So we're glad to be working with everyone. I want to take a minute to talk about this packet tracer in particular, because I know one of your classmates had a question about this 471, but I want to bring it up because I want to show you something that's important to note about packet tracers. This one is actually a PTPM or PPTM, packet tracer physical mode, or PTPM, that's it, PTPM. And what they're trying to do really is, some of our packet tracers are look and see packet tracers. And I don't want you to spend enormous amounts of time trying to figure out exactly what they're asking, when what this packet tracer is really designed to do. If you look at it, it's really showing you a small office or a home office. And it asks you to go in here and you read through it. It talks about, what an ISP is and how ISPs are connected. You can see it's a little hard to see, but there's a physical cable that's connecting to that PC right there that goes over to a wireless router and a wireless switch, or this is actually like a little cable modem that's coming in. And then here's your little wireless router that's come in, the home router. And so this is trying to show you, since we can't have a physical connection, or we're not in physical classroom together with one another. In a physical classroom, I would show you this. I would literally say, all right, so here's the little home wireless router. We connect that to our network and we go from there. But we can't do it. So what they're trying to do is give you and your students the opportunity to see this and to be able to do labs. There's Uzma coming in. So Uzma will be here in just a minute. So let's wait, just say, hey, Uzma, we're starting to go over this packet tracer you were having some issues with. And so what it is designed to be a look and see packet tracer. We can do a check results on it, but there's really not a whole lot there, because it just tells you completed the activity when we haven't done anything. And that's because this particular packet tracer is a look and see packet tracer. So what we're going to do is, it says, what is my IPv4 address? So it tells you what is an IP address. This activity opens inside the home network, and this is the home network. And it says, click on the home PC. So right there's the home PC. You click on it, and you will see it gives you the PC. It then says, go to the desktop and go to the command prompt. And at that command prompt, run the command ipconfig. And it will tell you that your IP address, this is 192.168.0.75. Then it goes on down and says, if you happen to be on a Mac, you would use a different command to see this. But it also says, next thing it says, what is the address of my router? Well, your router is always your default gateway. So your router's IP address is this 192.168.0.1. So this is showing that your home PC is connected to 192.168.0.1. And that is the router, and that's how we get out of our network. If this was a real PC or a real network, we could actually do like a route print, and we could actually see the default gateway and where it's at. But this is showing you that that's the default gateway. If you go down, it says, what is my public IPv4 address? Now, in the real world, you can run a command to find out what your public IP address is, and it's especially because we're behind multiple layers of IPv4 and IPv, NAT basically. But with this, it's having you walk through and use the tools. So if we go in here and close this and we go to the web browser, it tells you type in www.tellmemyip.com and click go. And this is all being simulated. There's a simulation going on. And so if I click go again, it takes it just a little bit to figure it out, but it's actually going to eventually tell me what my actual quote public IP address is. Well, it's supposed to. If I put, there it is. So it tells me my public IP is 1070.93.27, and that is through Comcast cable in Pacific Grove. It also gives me a fake geolocation. So this is trying to show you how you could do this. Now, actually, let me see. I'm gonna try www.tellme.com. I don't think that's a real site out in the real world. Nope, it's not. So there's no real way for us to do that in the real world. So this is all in the simulation, just trying to show you how you can do that by looking right here. Then he goes on down and it says, where examine the connections in your network. What does the connection look like between your device and your router? Is it wired or wireless? Now it's a little hard to see, but if you look, you can actually see the cable coming out of the back of this PC. You can see it going along the floor here. Another way you could tell this is by going into your command prompt and doing an ipconfig/all. And then this would tell you the name of the interface that has the IP address. And in this case, it is the fast Ethernet 0. So that tells me that it's directly connected via that cable. Again, we can also see it. We can see it connected right there. And you could, in this particular thing, you can't zoom in very easily, but you can actually zoom in, and then you could see that it's connected right there to that PC. Where's the router that your device uses to connect to the internet? Well, like I said, if you look here, you can see this cable going across here. You can see your wireless router right here that you can click on. And you can see the cable modem that is connected to that wireless router. So what this is really trying to do is just trying to get you to see how a small office or a home office would be set up. Then you can go in here and you can open up, and again, it tells you to do trace route from the command prompt. So we can enter, say trace RT www.hawaii.edu. You'll see it goes through and it shows you all the different hops because it's simulating all these hops to get over to hawaii.edu. Okay. And so it goes all the way through and gives you, eventually you may get a request timeout depending, right, it says around the 15th or 16th when it starts to time out.
Yeah, the trace route worked for me, Kelly, but the little office setup just went above my head. I didn't understand that's what I was looking for.
Well, and that's what this is. It's just trying to show you how it would be if you had a small home office. And then, really, again, as you're going down through here, it talks about notice home PC is connected to the home router on the shelf behind the desk. However, the home router is not connected directly to the router at the next hop. Instead, it's connected to the cable modem. Cable modem is not a router, therefore it is not shown as a hop in the trace route. In fact, you could say the cable modem is a layer 2 device, which is what helps it actually kind of move us towards our module we're going to talk about today. But this is a layer 2 device because it is converting from the physical layer, which is the RJ6 cable coming in for the cable modem, to RJ45. And it's also doing things such as framing. It's also doing things such as controlling information at layer 2. So that's what it's trying to do. And it also will show you as you're trying to change different, change your different hops. See, some of the hops have the domain name in it. Again, we're talking here about local loop. So local loop is from the local phone connection. So that's this connection into your cable modem. And it's just talking about the different pieces of a home network. Okay. Now you also have the ability to go back a level. And now that's what they're having you do here. Navigate to Monterey. You'll notice what they're doing here is you can go to Comcast's point of presence and see what's in this point of presence. So this is showing you where your cable, your actual network is connected. So this is going to the cloud, which goes back to your device. So here's your home, and this cable modem here is connected all the way up through this connection here to the Comcast point of presence. And then the Comcast point of presence, which is your local ISP, is connected to the Monterey, which is right here. And then you can see these devices right here. So you can see the different physical connections. So what they're trying to do is show you, here's a gigabit Ethernet from Comcast POP Monterey. And then here's a connection that goes, if you hover over it long enough, it'll tell you it's gigabit Ethernet but it's using fiber. Let's see if this one should be used in fiber too. So these are 2 fiber lengths that are going to the Comcast point of presence. So all they're really trying to get you to do is to see how these devices are connected together. And you can even go up here, and this goes up, and I don't think it actually shows what it does show you. It shows you how it goes all the way up to San Jose, down to Los Angeles, this underground cable, which is a submarine cable, which takes you all the way to hawaii.edu. And that's really all they're wanting you to be able to see, is to be able to see that these are the different pieces of just a home office. So it's very interesting that they've got you doing this. See, here's your trace route again, going back to that trace route. They've got you looking at the Monterey, and basically they're showing it go up this cable. They're showing it go up to San Jose, down to Los Angeles, across this submarine cable, all the way over to Hawaii. And that's really all they're wanting you to do. You're not, you're looking at your different domains. So look at hop 5. You can go back in here and look at hop 5 and say, okay, in hop 5, so let's go and look. So 1, 2, 3, 4, 5. Hop 5 was right there. I forgot to put I think I didn't do the trace route with the full command.
I noticed when I trace routed it on my computer, none of the names came up. I had 2 names come up, and the rest of them were just the IPs.
Okay. Well, what you could do here is, if you wanted to, you could look for the 5th hop. So you could actually go back and try to find. So there's one. We know that one. I'm going to go up to here. There's that should be the one that's going to your home, probably. Comcast. Yep. See, that's going to your cable modem. So that's telling you that this is actually going to the cable modem in your house. Here's the link going to the Comcast, and here, so there's hop number 2. We'll go over here. This is hop 3. And we'll have to go up one more level and see if we can't find. Oops. Up to San Jose. There's hop 4. And there's hop 5, sunnyvale.ca. And these are just, so it's showing you the different hops all the way through. And you'll notice how it's a fiber hop coming in, then there's a crossover fiber, and then it's going to the next one.
My question was, I haven't, like before, there is no name when I did the hop.
Right. And that's why if it doesn't show the name though, just count them out. Just go find it. I mean, you can go and find it by just looking at the number of hops. The 5th hop would be the fifth router it goes to, because remember, every time it goes to the router, it drops the TTL by 1 and then sends it out again. So let's see if they've got.
So that would dump our 5th hop as Santa Clara then, not Sunnyvale.
Correct. Sorry, you're right. That would be the 1, 2, 3. Let's go to Santa 4, 5. That'd be Sunnyvale. Because your first hop is in your house. There's hop 1. There's your router. Remember, this doesn't count because it's just a layer 2 device. So the cable modem doesn't count. So there's 1, unless I miscounted. Okay, so that's going there. There's a router. That's 2. 3, 4. You're right. Here, let me make sure this one goes. Correct. 3, 4. You are correct. There's 2 there. So it would actually be Santa Clara. That is correct, because of the 2 that are in the 2 routers that are found in down here in the Monterey, because there's 2 routers here. So that is correct. Good catch, Steve. But the big thing is here, I'm not worried that you know exactly which one it is. What I'm more worried about is that you understand that you're moving through each one of these as you move along the path to get to hawaii.edu. That's the more important thing, that you're understanding. And you also remember, one of the things we're going to see, and you've already seen, is that at layer 2, every time a packet goes through a router, it gets rewritten at layer 2. And so you've got to understand that every time it passes through, it's rewritten at layer 2. So that's really what is going on here and what we're trying to get you to see. Not so much that you can, know exactly which one's which, but that you know that that path is in there. Because here's what's going on. Here's the crazy thing. When you're in here, okay, let's look at logical mode. You can't switch logical mode because it's locked. But when you're in here, this is exactly what's going on in your house. Every time you go to any place on the internet, you're going to go through your local home router, up to your ISP's point of presence, which is right here, the Comcast POP. Now, there's a whole lot more going on here than this. And sometimes your POP may actually be on the side of the road near your house for a DSLAM or something of that nature. But then, then you're going to eventually get back to a point of presence that is at a service provider. And then those service providers connect to other service providers like such. And then all of them connect together across things such as submarine cables so that you can get across. This is literally a, they put out here in the middle of the ocean, a repeater, because in Packet Tracer, the fiber wouldn't run far enough to get across the ocean. So they put 2 little repeaters in here, and they actually do occasionally have repeaters on the underground cables, underwater cables. So that's the bigger thing for you to get out of this. Does that make sense? There's there's nothing for you to do here. You can't really go in here and turn anything in. It's, do you understand that you're jumping through each one of these in order to get from your house in Monterey all the way out to Hawaii?
Does the DSLAM count as a hop?
The DSLAM typically does not, because the DSLAM is a layer 2 device. Now, it depends on how the DSLAM is set up. Now, sometimes they do some routing out there, but most of the time, DSLAM is a layer 2 device. If you don't know what a DSLAM is a device associated with DSL. And so it's usually a layer 2 device that does your clocking and your rate limiting and all your circuit creation and those types of things on the DSLAM.
Yeah, I've seen them, and it looks like you get a bunch of 110 blocks inside this thing.
Yep. It's a layer 1, layer 2 device 99% of the time.
Okay.
And then it brings everything back to the point of presence, this Comcast POP, and that's where the routing takes place, is inside of here. Okay.
Thank you.
Mm-hmm. So let's see. Let me actually see something here. I want to see this server, see if I can get in this thing. I just want to see what its IP address is, because I bet you I know why our so this is 10.120.188. So I'm gonna go back a second. Nope, not that. It was 88, wasn't it? I think they had the wrong.
Yes, that was 88.
All right, I think they may have had the wrong. Let's see if that fixes the DNS issue. Maybe not. Nope, it's not wanting to convert it. Yes, that did not. Because that should be the reason you're not getting the names is because the DNS server on this should actually be doing your name. Oops. It should actually be doing the names, but it's not. Now, okay, so it did reserve it. For whatever reason, it's not doing the. 1 second, let me check something. CCNP Enterprise book I'm looking at. 1 second here. Does that make sense what I'm showing you with this particular?
Does for me.
Oh, wait a minute, having a cramp. Okay, so let's try this. I think, let's see if they implemented it. If it implemented it correctly, then, oh, see, they're not allowing you to do, not allowing the switch that actually allows you to do to resolve the host names, address of the host names. You can't do any of the switches at all. Oop. Yeah, won't let you do it. So, but that's really the big thing I want you to get out of this. I don't want you to spend, tons and tons of times. Realize we're looking at how do we connect layer 1, layer 2? How does this routing work? How do we move through this network? That's the important factors in this particular lab. All right. Any other questions? These again are look and see packet tracers. There's not much for you to upload. I still want you to upload it, but there's not a whole lot to upload here because it just shows you that it's there. In fact, I just had packet tracer just actually stop working for me. It's funny. All right. So let's talk. We talked about the physical layer system. Let's talk just a few minutes about numbering systems. I'm not going to spend a lot of time on this because I think most of you are pretty familiar with binary and hexadecimal, but let's talk a little bit about binary. Computers are extremely dumb. They know ones and zeros and that's it. They don't know anything else. So for everything that we put in dotted decimal format, computers see it in decimal. So we may put 192.168.12.1, but they see hexadecimal, or they see decimal, or excuse me, they see binary 1160s. So we don't use that because we're not good at binary, but computers are extremely good at it. Now, there's a couple things we need to know, and that is how do we convert binary to decimal, decimal to binary? Well, first off, what is binary? It's a base 2 numbering system, right? Agree with me on that one? Yes. Okay. What is our normal numbering system? What do we use? I was working my wife's network. What's our normal numbering system?
Base 10.
Base 10. Yep, base 10. So we use, and we are accustomed to a base 10 system. So we know that we have the digits 0 to 9, okay? And we use 10 to the 0, which is the ones, 10 to the ones, which is tens, 10 to the twos, which is hundreds. So if I say I've got $5, I'm really saying I've got 5 ones, okay? If I'm saying I have $110, I'm actually saying I have 1 100, 1 10, and 0 ones. That gives me $110. Why do we have a base 10 numbering system? I'm giving you a little hint. Say,
You got 10 fingers.
Got 10 fingers. That's the best guess we got is why we have a base 10 numbering system. Okay, so we have a base 10 numbering system. Computers are very dumb. Computers use a base 2 numbering system, which means there's only 2 digits, off or on. Okay, luckily for us, we don't have to go much beyond really 2 till about the 7th, but each one of these bit positions has a value associated with it. What is 2 to the 0 power?
1,
2.
1,
2,
2,
4, 8, all the way up, 2 to the 4th, 16, 32, 64, 128, 256, 512, so on and so forth. So with a base 2 numbering system, we have that. So what we're going to have to be able to do, or what we need to be able to do, is we need to be able to convert from binary to decimal in an easy way. Now let me show you the easy way to do this. It's called, when you're going from binary to decimal, it's called the addition method. So if I have binary of 1 0 1 0 0 0, that's 1 2 3 4 5 6 7 8, Okay. The correct way to convert this is you look at each one of these bit positions, to the 0, to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5th, 2 to the 6th, and 2 to the 7th. Now, what I usually actually teach my students during the beginning process of this, and in fact, even when I take a certification exam, I usually take the little grease pen and the grease marker that I have, and I usually write this out to the side just so I don't make a dumb mistake with conversions. And I usually go to about 2 to the 10th, but I do this 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So what I do is here, and when I look at this binary number, 101, 00010, the method to convert from binary to decimal is you look and see the positions that are turned on and you add those values together. So 2 to the 7th is 128. So it's 128 plus the 64 position is not turned on, so it's 0, plus 32 because the 32 or 2 to the 5th position is turned on, plus 0 at the 16, plus 0 at the 8, plus 0 at the 4, plus 2 because the 2 position is turned on, plus 0 because the 1 position is not turned on. And what is our value here? It's 194. And I know that because excuse me, not 194. That's, I messed that up big time.
160.
164. 164. Okay. Because 128 plus 32 is 160. 162. Good gracious. I'm butchering conversion today, y'all. Sorry. 162. All right. Finally. So 128 plus 32 is 160 plus 2 is 162. One of the things, if I had, how about 111100001, I would say 128 plus 64 plus 32 plus 16 plus, okay, now I'm at 0 at the 8, 0 at the 4, 0 at the 2 plus 1. What's my value here? What would that be? Little trick, 1111 and all zeros is 240, so this should be 241, unless I've done my math wrong. Somebody tell me if I'm wrong. So binary to decimal, we use the addition method. Pretty simple. Questions about it? So this is called the addition method, or addition. Okay, to convert. One of the things I teach my students too, folks, is I teach them this. If it's a 1, well, first off, it's all zeros. We know exactly what it is. It's 0, right? But if it's a 1 and 7 zeros, it's 128. If it's 1, 1, 2, 3, 4, 5, 6, 7, 8, it's 192. If it's 1, 2, 3, 4, 5, 6, 7, 8, it's 224. 1, 2, 3, 4, 5, 6, 7, 8 equals 240. 1, 2, 3, 4, 5, 6, 7, 8 equals 248. 1, 2, 3, 4, 5, 6, 7, 8 equals 252. 1, 2, 3, 4, 5, 6, 7, 8 equals 254. And then all ones equals 255. And one of the reasons we're concentrating on just 8 bits is because we're going to find out that, remember, our IPv4 addresses are 32 bits consisting of 8-bit octets. So this is useful because it allows you to do quick conversions sometimes. So if you see something that again is 1, 2, 3, 4, 5, 6, 7, 8, then you know that's 193. All right. The other thing you can do is this. If the last bit is turned on, it should always be an odd number. If the last bit is turned off or is a 0, it should be an even number. Okay. So questions about that, going from binary to decimal? All right. How about decimal to binary?
I use the cheater way.
I think I'm okay.
What is that? How do you cheat?
I do the same score with you, but on my vertical axis, I do the 128, 64, 32, and I just run that across as my top tabs.
Yeah,
And then I 1-0 all the way across, and that tells me what the value is to convert.
that's a good one too. Yep. Now decimal to binary is very simple too. It's the subtraction method. So I'm not going to spend much time here. That's this whole section. Basically, if you've got, let's say you've got, let's just convert for simplicity's sake, 10 decimal to binary. Well, first thing you'll do is, can I subtract 128 from it? The answer is no. So you put a 0. Can I subtract 64? Nope. 32? Nope. 16? Nope. 8? Yes. That leaves me with a remainder of 2. Can't subtract 4 from 2. I can subtract 2. And there we go. We've got 10 is 1010. All right, because we're going to leave off. It's a bigger number. If you've got, again, we could do a simple one, 192. Can I subtract 128? The answer is yes. So we put a 1. The remainder is 64. Can I subtract 64 from that? Yes, I can. So what I do is put a 128 here. That leaves us with 64. I can subtract 64 from it. Leaves me with a remainder of 0. So now I know that the rest of this is all zeros. 1, 2, 3, 4, 5, 6, 7, 8. So 192 is 11000000. All right. So I'm not going to spend a lot of time on this. I just want to make sure you know how to do it, because it becomes important as we move forward and we're working with our IP addresses, because we need to be able to do this. All right. Now, I will tell you this. The neat thing here is inside the curriculum, something that's very useful for your students are these little HTML5 activities, which basically says, give me the answer. What is the binary number? What is the decimal here? This is 255. And you can check it. It tells you it's correct. Give me a new number. And it will just keep making new numbers for your students. And so you can go in here and say, okay, so this answer is 16. All right. And so you can just do new numbers and let them practice and practice and practice. So decimal to binary is the subtraction method. Again, going in, if it can be subtracted, subtract it, turn that value on. If it cannot, then move to the next position. If it can be subtracted, add 1, subtract it, move on, and you go on, so on and so forth. So very easy for you there. The last item I'll just touch on momentarily is hexadecimal. Hex is a base 16 numbering system, and we will be using it when we deal with hex debts and IPv6 addresses. So that's an unofficial term, but it's one we all use now. But each one of these is a hex det with a value of 000 to FFFF. And we will talk about that much more as we go forward. Now, we really don't need to convert between these two, but if you are going to convert from decimal to hexadecimal, you really have to convert to binary first, then convert that binary to hex. And by doing that, you just convert it to binary and then split it into 4-bit groups, and then convert those 4-bit groups to hexadecimal. And just remember, hexadecimal, since it's base 16, uses the numbers 0 through 9, or the digits 0 through 9, and then A through F to represent 10 through 15. All right. Let's go to data link layer. Let's talk about layer 2 of the OSI model. Quick question. What are the 2 sublayers of the OSI model's data link layer? So we know we've got the physical layer down here. We've already talked about the cables.
Yeah, you got MAC and then the data link.
You got the
link
MAC.
layer.
The actual layer name is the data link layer. Okay. The 2 sublayers are MAC and what else? Should be the logical link control.
Oh, okay. Logical link. Yeah. LLC.
LLC. And remember how I talked about how now above this, we've got the network layer, right?
Correct.
And so the data link layer deals with physical addresses. It deals with physical addresses, which are our MAC addresses, which are burned into the network interface card. Okay. It deals with framing. Okay. It deals with access control. So how you get things onto the media or medium. Oh, that's terrible right there, but access control, CONTROL. And This obviously down here are physical layer components. So the MAC layer kind of is this go-between between the physical layer components. Well, up here, we've got to have a way to talk to the upper layer, because these up here, these are not physical components. These are all logical components. So logical addresses such as IP addresses. So the way that we interact with them is we interact using LLC. So we can rewrite the LLC for every new layer 3 protocol that we have. So the data link layer has this break that is kind of like the break between the physical and the logical components in the OSI model right there. The OSI model, the data link layer, again, deals with the ability to do access control onto the media. So we're going to learn about 2 different types of access control. We'll talk about the carrier sense multiple access collision detection and then collision avoidance. But here we have our layer 2 addresses that are very important. These are burned into the network interface cards for most of them. Now we do have virtual MAC addresses now because of virtualization, but in the old days and for traditional looks at the media access control addresses, they were all burned into the NICs. And so here we have again the sublayers. So we've got our different MAC, the MAC sublayer, so that we can run wired Ethernet or wireless Ethernet or run over Bluetooth. And then we have a logical link sublayer 802.2, which then can talk to our network layer so that we can run any type of layer 2 protocol and still run IPv4 or IPv6.
Hey, Kelly.
Yes, sir.
This is I don't mean to digress.
That's
But
okay.
have you heard about Google and saying they're coming out with a new transmission that's supposed to be faster than the present TCP, and that something about that may be going away? Have you heard anything about that?
I have not heard anything about it. And one of the things I would say to that is yes, but, and the reason why is this. Think about the fact that IPv6 has been around since 1999, and technically IPv6 is faster than IPv4, because we'll learn as we move a little bit further down in the network layer, we'll see that the header is actually smaller for IPv, well, not smaller, it's simpler for IPv6 and IPv4. So technically IPv6 should be faster than IPv4, but the problem is all of us have all of these devices that run on IPv4. So I would find it hard to believe that anything is going to take the place of TCP/IP for a good long while. Having said that, I could see it taking a place maybe on some IoT or smart home devices. In other words, they may develop an internal protocol that runs more at layer 1, layer 2, maybe layer 3, but is then converted into IPv4 when it gets out on the internet. I could see that, but I haven't read any of that. Be interesting to see though. So looking at providing access to medium. So what we have to do at layer 2 is we have to accept the frame coming in, and we have to look at that frame to see if it's actually destined for us. And you'll notice that as the route goes through every router, that layer 2 header is re-encapsulated. So it comes in, the router brings it in, de-encapsulates the frame, and then re-encapsulates the frame in whatever is needed for the next hop. So in this case, it came in on an Ethernet connection, it went out on a serial connection. And so the router rewrote the layer 2 information at every hop. That is a key point, and was one of the reasons I made that point when we looked at our packet tracer. The standards for data link are typically handled by these organizations, IEEE, ITU, because these are more physical layer, closer to physical layer components. And so they're handled by these organizations. So topologies, different ways that we can do connections. And that is, we have the difference between a physical and a logical topology. This is the physical topology, the way the devices are actually connected to one another or cabled to one another. The logical topology may be different than that. You'll notice these are all cabled together, but these devices are in their own little network over here. The best example of this where logical and physical topology were different were back in the old days, because back in the old days we had token ring networks. And so we had a switch here that was actually, it wasn't even a switch. It was like a token ring MAL, and that's called a multi-station access unit. And you would put PCs off of this device. Okay. And so physically, this looks like a star, but logically, it was actually connected as a ring so that you could do token passing inside of here. Now, our networks today are typically a little more in line with this. In other words, they're physically stars. Logically, they still act like buses because of the way data moves. But the logical topology and the physical topology can be very different, which is important to note so that you can figure out how these devices actually connect together. So although you have all these switches, they're actually in different logical networks, even though they're in the same physical space. WAN topologies, we really have much simpler connections. We have point to point. We have what's called a hub and spoke, which is you've got a central hub with spokes off of it. And then the satanic mesh network, which is your pentagram, which is all of them connected together. I will tell you this, mesh is your most resilient as far as for failures. But the reason we don't run full mesh networks to everything is because of the cost. Imagine having to pay for every one of these physical links in your network. And you can see how that could become very expensive.
No, the wire weighs a ton.
The wire weighs a ton, and it costs a ton. You know, even if this is all fiber, which is not very heavy, it's expensive. They're on campus right now pulling fiber to replace our campus fiber network. And the cost of that is enormous. So point to point, obviously node 1 to node 2. Now, one of the things people don't realize that many times across a WAN network, even though it looks like it's point to point, what's really going on is inside of here, you may be running your service provider may be running MPLS, which is multi-protocol label switching, or some other type of tunneling protocol. You can even, there's GRE, generic route encapsulation, and there's PPT, not PPTP, but VPN protocols. Oh, somebody help me out. Just totally drew a blank on the most famous, the tunneling protocol. But either way, it is possible to go across the network with VPN tunnels and make it appear like you've got a point-to-point link when you really don't have a point-to-point link. Okay, here's our LAN topologies. Again, the star is probably one of the more common in small networks, with extended stars being what we use in most modern networks. In other words, we would have a switch that sits in a data closet, and then that switch connects via a home run link to another switch. Or you could have two switches right in the same data closet, just have a jumper between them. And then you have a home run link all the way back to a point of presence on the campus. That's how we do here. We have a closet that has our switches in it in our data center. And then we have a fiber run that goes all the way down to the main campus point of presence, and it plugs in there. Here's an old school bus. Back in the old days, we actually had physical and logical buses. So we would take RJ58 cable, and that cable would then have a terminator on each end. Back in the old days, if the worst possible thing you could have is when this cable broke, it actually took the entire network down because signals would bounce back and forth. So you'd have to walk around with a terminator in your hand and put it on, see if it fixed the network. If it did, then you know the problem's that way. Then you would move one over, put terminator on, check it again. So we don't want to go back to those days, trust me. And then I've also worked on ring topologies back in the day of token ring. Token ring, quite honestly, as an access method, was better than our methods today. But because of the fact it was proprietary and IBM would not allow third-party vendors to create NICs and things, that's why it was so expensive. And Ethernet just got faster and faster and faster. I make some jokes here about this, but if you've ever watched National Geographic about, it's always the British guy on Mount Everest, base camp to camp 2, over. Why do they say over?
So you know it's your turn to talk.
Your turn to talk. Walkie-talkies are half duplex communication. You can either send or receive. That is what is meant by half duplex. There's actually another type of communication called simplex they don't mention here. That's when it's going one way only, so send only, no ability to receive. But half duplex is you can send or receive. And what happens is you've actually, the way it's wired is your sending wire is connected to the receiving wire and vice versa, so that you can't send and receive at the same time. With full duplex, which is what we have with our cell phones, you have a sending pair of wires and a receiving pair of wires, so you can send and receive at the same time. Our goal in life is for our networks to always have full duplex. That way you have the fastest speed available. Now, I told you the data link layers are designed, or it's designed to do access control. So how we put things onto the media. There are two types of main access control. One is contention based. So if your students ever have problems thinking about what is contention based, the way I explain it to mine is this. If you are in competition with someone, you are in contention with them. So a contention based access method means there's going to be competition for access to the media or media. Controlled access means there's no competition. Someone's in control. There's a cop or a data passing or a token passing mechanism that says you have control, you can talk, or you have control and you can talk. Our contention-based methods, the two primary ones are carrier sense multiple access with collision detection. That's the old school Ethernet method, and it works like this. Carrier sense, listen to see if the line is available. If it's available, then send. So that's the carrier sense with multiple access, because everybody could technically listen. There could be nothing on the line and everyone could send at the same time. So multiple access is allowed. If two devices send at the same time and there's a collision, boom, they hit each other. What happens is the creation of a collision runt, which is actually a frame that's smaller than 64K. Every machine that sees that will then say, whoop, oh, there's been a collision. Everybody perform the back off algorithm, which says wait a random amount of time before you try to resend. Now, the reason you want to wait a random amount of time is because you don't want it to be wait 10 seconds and resend, because otherwise it'd just be constant. It'd be like the Rams on that National Geographic picture where they keep hitting each other in the head with their horns. So carrier sense multiple access with collision detection listens. If the link is open, sends. There's still a possibility of collisions. If there is, you have your collision detection mechanism using the back-off algorithm. Traditional Ethernet bus-based legacy topologies use CSMA-CD. CSMA-CA collision avoidance works exactly the same, except for you listen to see if the wire is available. If it is, you request to be able to send. And then, because it's usually wireless, the access point will say, you're clear to send, you send now. And so the idea is there should not be any collisions. But if it does, if there happens to be a collision on a collision avoidance network, it works just like CD. All right. And back in the old days, if you ever read the book, Lord of the Flies, not Lord of the Rings, which is a better book in my opinion, but you know, everybody's opinion is different. Lord of the Flies is where the British kids are on the crash landing on the island, and they have the little conch shell that when they have their meetings, if you have the conch, you can talk. Token passing is a controlled access method that is like that. If you have the token or the conch, you can talk. If you don't, you cannot. It was really a better method. It was a lot better in carrier sense multiple access with collision detection, because with controlled access, there were no collisions. The problem was it was 10 megabits and then 16 megabits. And while they were arguing about that, even though they were getting 16 megabits per second and there were no collisions, Ethernet was saying, you know what, we'll just speed it up to 100 megabits. If we have collisions, no, we'll just retransmit. So they were still getting sustained rates that were higher than what Token Ring could get. But just need to know it as a legacy type thing, controlled access. All right, and I've talked about these a little bit, about those. So let's look at a data link frame. Let's look at what is in a frame. The frame has a header, data, which is all that information from the layers above. Remember our Russian doll analogy that I gave you? It's all that information above. And then there's a CRC or a trailer at the end. So here's our frame field. So in this header, there's a frame start delimiter. That's a series of bits that are used to identify this as the beginning of a frame. The addressing is here, which is going to be your destination MAC address and your source MAC address. If you're running Ethernet, if it's not running Ethernet, it'll be whatever is needed for the media that you're going across. type, which shows you what layer 3 protocol is in use. So it tells it where, by the way, this type field works with LLC to tell it where to pass it to up above you. Control, which is if you have differentiated service control points or quality of service issues or items, they're all in there. This data that's part of the all the other information, which is layer 3 through 7 above it. And then you've got your error detection, which is your CRC or your cyclical redundancy check or frame check sequence. You see it listed as both. And then there's a frame stop sequence at the end, which is a series of ones and zeros that says the frame is over. So if we look at a frame, let's see if I got Wireshark on here real quick. Yeah, I do. Let me grab one and just show you a frame real quick. Do a quick capture. We should have tons and tons of, I'll remind me later. I should get tons of data. Yep, doesn't take long to get a whole bunch of information here. Oops, clicked the wrong thing. Give me 1 second, folks. So here's Wireshark capturing data on my network. It's probably firing off every IPS sensor in the entire network. But if I go in here and look at this, I can look at the Ethernet frame, and you can see here's the Ethernet information, and it tells me, by the way, looking at the frame here, here's our interface, the frame when it arrived. Here's the frame number, the frame length. It's telling me here's our destination and source MAC addresses. So there's the destination MAC address. By the way, a MAC address is a 48-bit address. The first 24 bits is what's called the organizational unique identifier. This is why this can say Dell 37, because it knows these first 24 bits have been assigned to Dell. And down here, by the way, this tells me that this is a frame between a Dell machine and a Meraki machine, a Cisco Meraki switch, or some type of Meraki, because this is saying Cisco Meraki. So the first 24 bits are the organizational unique identifier. The last 24 bits are a serial number. Benjamin, do you have a question?
So I assume like when we get into the cybersecurity ethical hacking, this is like the first step they would need to know.
Yep.
This is where they start at ground zero.
Yep, this is ground zero. This is, by the way, anybody remember the bind, torture, kill killer, BTK killer?
Yeah.
The way they caught the guy was Word. He sent a manifesto in a Word document to a newspaper. What he didn't realize is Word at that time in the metadata embedded the MAC address of the machine that it was created on, that the document was created on. The FBI got a hold of that document, looked, found out it was a machine sold by Dell, went to Dell, found they suspected the guy anyway, but they had no proof. Found out that it was made by Dell, went to Dell with a subpoena and said, we need to know who you sold this MAC address, this machine with this MAC address to. Lo and behold, it was sold to this person. Boom, they caught the BTK killer. So that's one of the things that I joke about needing to always have a throwaway network interface card. Just joking, folks. But one of the things about that is true. Think if you lived in a society to where they're trying to kill you or find you and prosecute you because you're against the government or whatever. If that was being embedded, that's one way they could easily find you, is because that does come all the way back to you.
Well, that's tip number one of living off the grid. If you got a mobile phone, you get disposable SIMs. You make your call, you break the SIM and put a new one in so they can't get a tag on you.
That's why if you ever go to a yard sale and they're selling old wireless network interface cards, just grab them. Yeah, I'll give you $1 for these. No, I'm just kidding. But that is something important to note, that it is easy to track this back, and that is how we can find certain things. Now, you also can spoof these. So don't think for a second that if your hacker's really good, they're going to be spoofing all their MAC addresses or as much as possible, or using botnets. But still, you'll notice here's our type. This tells that this is being passed up to IPv4 0x800. And then you can see that this has got the IPv4 information. So every single one of these is a frame, and every bit of that's got that information in it. So there's a source and destination MAC address. Notice the destination MAC address is first, then the source. And the reason for that is because as we look at this process here, when something comes into a device, the very first thing it has to do is take it apart and look at it and say, is that my MAC address? If the answer is yes, then it passes it up to whatever the next layer protocol is based upon that type field. And then if it says, is this the destination IP address? Is that my IP address? If the answer is yes, it continues to pass it on up. So that's why they put the destination MAC address first in frames, is because they knew everyone. And by the way, in old networks, back in the old days, in the very old days, this is how we would have a network. We'd have, the cable wouldn't be quite that curved, but we'd have computers on here, right? So there's a computer, here's a computer, here's a computer, here's a computer, right? So this is, we'd have a terminator here, we'd have a terminator here. So back in the old days, this is a true bus network. So A, B, C, and D. So A listens, the line is clear, carrier sense, multiple access, sends. So it's going to send something to D. So it puts in the destination MAC address D. We're just going to send, for right now, just I'm going to wave my hand and says it's got that MAC address. It's going to send that out. But that's going to come down here. It's going to go this way on the line. The terminator will get rid of it. By the way, what happens is it converts it to heat. Very, very minuscule amount of heat because it's very little current, but it does convert it to heat because energy can be neither lost nor created. It then goes this way. Once it gets to B, B takes a copy up to here, looks at the destination MAC address, says, whoa, wait a minute, that's not my MAC address. Throws it in the bit bucket. It keeps going. Goes to C. C has to look at it at least up to layer 2. It's not my MAC address. Throws it in the bit bucket. Goes all the way down. It actually keeps going all the way here. D grabs a copy. Now, it again, here it gets converted to heat, goes away. D looks at it and says, oh, that's my MAC address. It will then pull that header, take it apart, and pass it on up to layer 3 or whatever, and then we'll eventually respond. But because every single device on this old school bus network had to look at it at least to layer 2 when they designed Ethernet, that's why they put the destination MAC address first, so that the devices wouldn't have to look any further than they had to determine if it was for them. Now, if you send something to the all F's MAC address, or which is like a cat, you know, if you send it all F's, everybody has to actually break it apart and send it on up because that's a broadcast, right? So that's an important reason if you ever want the historical basis for why the destination MAC address is first, that is why, because it made things more efficient back in the old days. Okay. Notice again, every single hop, the router is rewriting layer 2. It's not rewriting layer 3, unless we're doing that, which we're not doing in this class right now, but it is rewriting layer 2 at every single hop to match the source and destination layer 2 addressing. Here we have a bunch of different layer 2 protocols for, here's wireless, we've got serial, we've got basically through every one of these hops, it's going to create, here's an 802.11 frame, then it's going to become a HDLC or PPP frame, point-to-point frame, then HDLC, then frame relay, then Ethernet. So at each one of these hops, because it's changing layer 2 protocols, it has to be rewritten so that it can travel across that media or medium. All right, questions about this? I would like for you to go ahead. I do have lectures in here on 7 and 8, okay, 6, 7, and 8. So I would like for you to watch 7 and 8, and I'll have you one for 9. I'll get that up by next week too. But I'd like for you to go ahead and watch 6 and 7 and 8, and then next week let's talk about actual switching and how switches deal with layer 2. How's that sound? I'll give you a little more time to catch up a little bit, and we'll try to keep working forward. Okay.
All right. Thank you so much.
You're welcome. Anybody have any other questions? I'm gonna stop my share. Any questions about the class or any issues?
I
Not an
have one
issue.
question.
No issues.
Okay. Usma, go ahead. What's your question?
So there is an exam from module 1 to 3. When I have to complete that one? I did not do that.
What's the lazy
It was due. I had it due.
And I haven't read through everything.
what,
I'll have to
last
go
week,
through
I think.
item by item.
But it's
I don't
okay
have
if
a
you want to
lazy
go ahead
Susan.
and just take it. That's fine. It should be on for you.
I
By the
gotta
way,
go
this
through it
is-
item by item.
I got to
Oh,
call her.
okay. I
Okay, but
thought
I wanna
because
see
can
what-
take whenever I want. That's why I didn't take
yeah,
it.
yeah. But I do want to show you something though. This is an important point. Steve, I muted you. I'm sorry, but I'll unmute you. The exams in the class, as an instructor, one of the things you have to do is turn those exams on for your students. So when I go in here and look, I can actually show you that right now all of the chapter exams are on for you. but you will have to learn how to create activations, and you can create activations for individual modules or all of them at one time. And when you create activations, you have the options of creating an advanced activation, which lets you change the options here. So how long I give you, the chapter exams that I give you is I'm allowing you to take them up to 10 times each. I'm not using these exams to give you a grade per se. I'm using it for you to learn the material. So feel free, if you take it one time and bomb it, take it again. It's okay. I want you to take them multiple times so that you learn the materials and use it as a learning, basically a learning item instead of an actual assessment item.
Okay, thank you.
You're very welcome. All right, any other questions?
No question. I'm still playing catch up a little bit, Kelly, and just a reminder, they're doing my surgery in the morning.
Okay.
So I should be lucid,
Yeah.
as good as I can be come Thursday, and I'm back in, and I've been trying to play catch up, as you've seen by all the stuff I'm dumping in.
Okay, no problem. And the other thing is, I did post for y'all this O'Reilly Media database. I think, let me share my screen again here. I'm gonna share screen too. I posted this for you. This is an additional piece of resource that you have because of Stanley Community College. We actually have a campus subscription to this database. Every student who has a Stanley email address has access to this. You will notice that I have for you a playlist that has all of our CCNA items on it. So you can actually go in here and look at under CCNA. There's the 2 official cert guides, portable command reference, an entire video course. So if you don't like me and you think I can't explain things well, go listen to Kevin Wallace. There's an entire class here that's available for you that you can watch that goes through hours and hours of video. I do have an exam cram here, but the other thing is this you will have access to for at least 2 semesters past the end of your last class. So let's say that you don't take any more classes for us for some reason, and I expect all of you to go through all of them, so even through the fall. But let's say that for some reason you wanted to learn about AI. Okay, so that's artificial intelligence. Well, inside of here are just tons and tons of resources on AI. Resources on, somebody give me a topic. Give me any topic.
Blockchain.
Octane?
Blockchain.
Blockchain. Oh, we got that. Blockchain. Oop, if I spell it right. Blockchain. So here you go. Mastering blockchain, getting started with blockchain. Here's a video course on blockchain. What is blockchain? So these are your resources to use as you want. Okay, and the login, the way to get into it, watch this video right here, and it explains in detail how to get into this resource, and you can use it as much or as little as you want, and you have access to it as long as you have an active Stanley Community College email address, which is going to be at a minimum 2 semesters past the end of your last class you take with us. I paid $50 a month for personal access to this. And so in some ways, it's almost worth taking a $195 class from us just to maintain access to this database.
Started to say it's worth the expense.
Oh, there's so much material here that you couldn't get through it all if you wanted to. I mean, you really could.
Wow.
There's Ansible. You know, one of the things that I'm very interested in are containers. So here's a bunch of information on Docker containers. And learn Docker containers in a 1-hour video course. Okay. The other thing they do here sometimes, and this happened the last time, let's see, I think it was in my CyberOps playlist. Before it came out, the CyberOps book was actually inside of here. But now it's came out. A lot of times they'll do first, I think it's called first looks or first impressions. So sometimes you can go in here and search and find early releases. And so these are books that aren't even released as books yet. So this book is really not going to come out till September 2022, but here's an early look at it. So it's kind of a book in development. I can't say enough about this particular database and how amazing it is. So,
that is amazing.
all right. So it's available for you, and you can use it as much as you want. So, okay, everybody, I'm gonna stop